So welcome. I forgot to put a timer on my morning class, and it overran. So I'm not able to load it onto the YouTube as it stands at the moment. So I need to put a timer on here to make sure that doesn't happen again. So I'll put a 50-minute timer on, and we'll go from there. Okay. So we're going to talk about magnetic fields. So we've talked about electrostatics, and we talked about really electrodynamics, which is current electricity. Now we're going to talk about magnetism, and then we're going to link the two together. We're going to talk about electromagnetism, and that actually leads on to light. So we kind of work our way through the rest of the semester in kind of a logical sequence. Magnetic fields are a kind of weird situation because most kids play with magnets. So people are kind of familiar with magnetism, although it's kind of vaguely familiar with magnetism. And it is one of the less accessible parts of the curriculum. It's a bit mysterious. It's a bit harder to visualize. The equations are a little bit more complicated. But with steady application, progress can be made, and it can be fascinating. I know people who spend their entire careers looking at magnetism, and they're enthralled by it. So let's make a start. So we're going to talk about in this lecture is we're going to talk about just the idea of a magnetic field, and then we'll talk about the effects of B on a moving charge, and then we'll talk about application of the fine beam tube, comparison between magnetic field and electric field, and then we'll remind ourselves of the situation when we have two vectors that multiply together and give us a vector, which is a vector product, or the so-called cross product. And we're going to use that in a lot of cases. So we have the force and a thing called the magnetic dipole moment. So that's where we're going to go. You've either just done a lab, or you're going to be doing a lab where you plot out some magnetic fields. It can seem trivial, but again, it's like, these field maps are really quite informative, and the more we think about them and the more we can predict them, it's like building up the magnetism intuition. So we kind of like making expectations of what's going to go on. We have our magnet, of course, and we'll talk about how magnets work in a bit, but let's just say this is mysterious piece of metal that creates this magnetic field. And if you were to take a magnetic compass, like the thing you use for orienteering or navigation, you'd find that it points, and you could plot out all the directions. You just follow one of these lines, and you find that it starts at one pole and it ends at another pole, and we can plot different ones, and we get these. It's like an apple core, isn't it? It looks kind of like a bit like an apple core. Sometimes the magnetic flux lines, magnetic field lines, are close together. Sometimes they're far apart. And yeah, that's like it was for electric fields. When they're close together, that's a strong magnetic field, and when they're far apart, that's a weak magnetic field. So that same conceptualization can be applied to magnetism as it was applied to electrostatics. And we like to put directions on these things, just as we had a electric field by convention went from the positive charge to the negative charge, so we could tell which way around things were. We've got to have a convention for this, and so we say, well, the magnetic field points from the North Pole to the South Pole outside the magnet. We need a way to remember this, and the way that I was always taught was you point your finger. So here's my finger. And then here's my other fingers. Is that right? That's one too many fingers, isn't it? Okay, there's my finger. Here's a nice laundered shirt with a little thing. And so this is your finger tips. Tips. And this is, what's this called?
The knuckle.
Your knuckle. I know, I can't spell. Okay. It's a silent K, yeah. So from north to south. So we go, there's the North Pole, and we point from the north towards the south, outside the magnetic field. So that's just some conventions. There's no physics, you cannot derive that. It's just somebody had to decide, and so they decided, and that's the end of it, yeah? I keep saying in the outside of a magnetic field, which raises the question of, well, what about the outside of a magnet, which raises the question of what about inside the magnet? And here we have to draw some distinctions, which we'll dwell on later, but in electrostatics, the arrows start at the positive and they end at the negative, or infinity, we say, or infinity, whatever. You know, but they start at one charge. Whereas, for reasons we'll get to, magnetic field lines are loops. So inside the magnet, this field line continues. And that field line continues. Now this is a bit strange. This is quite striking compared with the electrostatics. Whereas in electrostatics we had poles, you know, a positive pole and a negative pole. And you could, in principle, rub a material and take the positive charges and put them in a box and send them back to Europe. You know, you can effectively separate them. You could put them in a box and send them to the moon. You could put them in a box and send them out of the solar system. And although they'd still all exist, they'd be separated. If I try and cut the North Pole out of a magnet, all that happens is I end up with a north and a south and a north and a south. And if I try and cut that north out, I get a north and a south and a north and a south. Every bit of magnet has a north and a south. And that is just, you know, that's just uncomfortable. If it's a thing, why can't I separate it? You know, positive charge, I could take it somewhere. North Pole, I can't get rid of the South Pole. And I think the way around this is, and we deal with it all day long, you never go home and worry about the fact that the front of the page cannot be separated from the back of the page. You never say, oh, I could take the front of the page and send it to Australia, but the back of the page is going to stay here in America. They're two sides of the same thing, aren't they? They're two aspects of the same thing. The page is the page, and you look at it one way, you see the front, you look at it the other way, you see the back. And it's kind of like that with magnetism. It's an appearance of something. So in a way, it's quite mysterious. It's like it's very, very. Can you see how it gets fascinating when you really get into it? It gets quite fascinating. So we say the SI unit for magnetic field B. Why not M? Because we've used M about 3 times already. So B. Magnetic SI unit for the magnetic field is the Tesla, named after not the automobile but Nikola Tesla. The big T. Frankly, before SI units became so prevalent, people would use they actually used to use CGS units and then MKS. MKS is very similar to SI. But in the past, they used the thing called Gauss, named after Gauss. And a Gauss is a really small unit compared with the Tesla. So what we find is that the Teslas probably a bit bigger than most people would like. We have this thing about numbers going from about 1 to about 100, and we feel very comfortable with it. And as we go further, as we go smaller or larger, we feel less and less comfortable. But, you know, having a magnetic field of a few Tesla is pretty good. So Gauss was a very natural unit, but it didn't get derived from SI units. So, you know, when the SI system came in, they said, all right, we're going to name it the Tesla. Magnetic poles are designated north and south. Single magnetic pole has never, and I don't believe, the book's kind of a coy. They say it's never been isolated, and I don't know if that means that there's a theoretical hint that they could be, or whether that means that they're just not prepared to say they never will be. I don't know. I don't think they ever will be. I don't know of any theory that says they can be. Magnetic field can be represented by magnetic field lines. Magnetic field lines form continuous loops, and that's whereas in electrostatic they started on one charge and ended on the other. That's no longer the case. Magnetic field lines extend from the North Pole to the South Pole in the region outside the magnet. So, okay, I've got I'm going to tell you about a couple of hand rules. And my favorite, frankly, is the bottom one, but most people get taught the middle one, first of all. So what this says is that it's a right-hand rule, so I'm sorry, all you lefties have to just get used to it. So there's my hand. And the thumb is the motion. Oh, sorry, I should tell you what this is about, first of all. This is about the force felt by a charge, electrostatic charge, when it moves inside a magnetic field. So we're already talking about the interaction of electrostatics with magnetism. What we find is that there's a curious thing happens. When you get charges going into uniform magnetic fields, they form circular paths or helical paths. But there's a circular aspect to them. And that's very indicative of a force that is at 90 degrees to the motion. Now, electrostatics, your motion and your force and your field, you could fire it in, but it wanted to, like throwing a football, it wants to eventually go downwards, yeah? Well, with electrostatics, it's like that. Downwards or upwards, depending upon the charge. Whereas with magnetic fields, things want to go in a circle. And that's usually indicative of a centripetal acceleration, and that means that some force is at 90 degrees to the motion. That's how you get circles. When some force is at 90 degrees to the motion, which sets up the centripetal acceleration, which is at 90 degrees to the motion. And so that's where we're headed. So what we find is that magnetic force is, well, it depends on the amount of charge. If you've got more charge, you've got more charge to interact, so a bigger force makes sense. And then it's this V cross B. And remember, that's a force of magnitude of V times the magnitude of B times the sine of the angle between, yeah? That's what FB stands for. Remember, what was the other physics 1 aspect that used cross product? Torque. So this is mathematically similar kind of games we're going to play as we played with torque. Okay, so I have 3 vectors basically. I have my V vector, I have my B vector, and I have my F vector, my force vector, and I want to link them. So hold your right hand up. Hold your right hand up and look at your thumb. That is the motion. That is the motion of the charged particle. We're going to assume a positive charged particle. If it's negative, just reverse your answer. Okay, so do it all for positive, and then if it's negative, just it's the opposite. Okay. Your fingers. Magnetic field. Remember north to south, your finger pointing? So this is your mag field. And then just hold your hand up. Go slap on the side of your face. That is the force. Force. And some people do the 3-finger version, where they, the thumb is the motion, and they only point one finger, and then they have the second finger points downwards, and they do it like that. Yeah, okay. Right hand rule. That works great for when things are orthogonal, when your motion is at 90 degrees to your field, and your force is then going to be at 90 degrees to both of those. Supposing that my motion is in that direction and my field is in that direction. If you try kind of bending your fingers, it kind of hurts sometimes. And so people come up with a generic rule of thumb for any cross product. And I think we did this in Physics 1. And that is, with your right hand, you point towards the first vector, and then you pivot your hand so you can curl your fingers towards the second vector, and then you see which direction your thumb's pointing. So I'm going to pause there, and we're going to practice. So we can say the magnetic force vector is given by F equals Q V cross B. Consequently, the magnetic force is perpendicular. The magnetic force is perpendicular to the plane containing the velocity vector and the magnetic field vector. And notice that I'm actually talking in terms of the order of my cross product from the very beginning. Consequently, the magnetic field changes the particle's direction, but not its speed. So if you have a particle in a magnetic field, it goes in a circle, but it does not speed up. The way you speed up is if you have a certain velocity and the acceleration is like in the same kind of direction. Then you speed up. But if your velocity is like that and the acceleration is like that, then you don't speed up. So, okay, so you don't speed up, and that means that the half mv squared for the electron does not get bigger, so you're not getting more energy, you're just redirecting the direction of the particle. The sign of the charge affects the direction of the magnetic force. So yeah, if you have an electron, it's going to have an opposite force to the positive charge. And then we often want to know the direction of the magnetic force will act on the moving charged particle. We can use various right-hand rules. Let's just review cross products. So what we say is for a cross product, so-called cross product or vector product, we say, and I make these really big. I used to use dots and little things, and I started noticing I made mistakes sometimes. So now if it's F cross D, F dotted with D for work, I make that big. And if it's R cross F for torque, I make that big. So I really emphasize those two symbols because I don't want to make a mistake. So vector A crossed with vector B as a magnitude, this is the magnitude of the magnitude of A times the magnitude of B times the sine of the angle between them. Okay. And we can say A cross B gives me a vector C. Well, this vector here. There. And it's at 90 degrees to those two. So I'm going from A cross B, gives me that guy. Yep. A vector product is not commutative. So A cross B is not the same as B cross A. So that's interesting. The order matters. And then the second thing, vector product is distributive in multiplication. So A crossed with B plus C is A crossed with B plus A crossed with C. And then if A and B are perpendicular, then the sine of 90 equals 1. So it's just the magnitude of A times the magnitude of B. The magnitude of these two guys is the magnitude of the two vectors multiplied together. And A parallel to B, well, parallel sine of 0 is 0. So if the vectors are parallel, no effect. If the vectors are perpendicular, maximum effect. Opposite to dot products. Opposite to dot products. And then there's this little thing here, which is we're only going to introduce it just so that we can use it in a derivation. What we say is, if you differentiate A cross B with respect to time, you get A crossed with dB by dt plus dA by dt crossed with B. So just you don't need to remember that. It's just there. Let's play with this a little bit more. And what I found was when I was a student, I just looked at this and said, I'm out of here, who cares? And as I've got more experience, what I found is that the more comfortable you are with the little stuff, the big stuff kind of takes care of itself. So don't underestimate the little stuff. The big stuff is just a whole bunch of little stuff put together. Okay? If you just concentrate on the big stuff, you're trying to remember how to do the big stuff. And I'm never going to ask you those questions. Well, I will, but not necessarily the same question. Well, not the same question, but not necessarily even the same layout of the question. So watch out. So we say, remember that ijk, that's a unit vector. So we say, okay, if I have I crossed with I, so that's that crossed with that, or j crossed with j, that's that crossed with that, or k crossed with k, they're all parallel to each other. So the cross products are going to be 0. There's no vector, or if you like, there is a vector of 0 magnitude perpendicular. If they are at 90 degrees to each other, it depends upon the sense whether it's a positive or a negative. So if it's I crossed with j, so let's do this. Let's point our fingers in the x direction, and then let's turn our hand and curl our fingers in the y direction and ask ourselves which way is our thumb pointing. And our thumb points in that direction if this is x and that's y, so that's A and that's j. I crossed with j gives me that direction. And that is a k. It's in the z direction. So I crossed with j equals k. And minus j crossed with I gives me a k. And j crossed with k gives me an I. And minus k crossed with j gives me an I. And k crossed with I, etc. So play with those a bit. Just don't be stymied by ijk and vectors. Just play with them. The signs are interchangeable. So A, well, let's try this. If that's A, if that's A and that's B, and say that's minus B then. So A crossed with minus B is going into the page, like you see in the arrow leave you. And minus A crossed with B is going into the page. Are you familiar with those two? So that is coming out of the page, and that is going into the page. Are you comfortable with that? This is like an arrow. And when the arrow's coming towards you, here's the feathers at the back, here's the shaft of the arrow, and here's the little pointed bit. So when you look, the pointed bit's coming to get you, so it's coming out of the page. and the arrow's leaving you, so you see the shaft at the back. You see the tail feathers at the back. So that's the terminology. Okay. So okay, that kind of makes sense. And then component form. Well, if A is equal to AXI plus AYJ plus AZK, and B is equal to that plus that plus that, then our cross product is given by this guy, and I kind of hate this because it's kind of like just coefficient nightmare. So let's just learn how to do it. So let's do one. And I did this before with you, so we'll do one to remind you, and then we're on our way. So what is the vector product of V cross B given that B is equal to? So I'm going to do IJK, and it's B cross V. So I'm going to put B down first, and I go 3, 4, minus 2. That's my V. And then my B is, oh, I just did that. Yeah, sorry, didn't read. Bad Bonacristi. Let's go back here. So remember, I'm doing V cross B. So I've got to put my V down first, and my V is this guy. So that's 2 minus 3 plus 3. That's my V. And my B is 3 plus 4 minus 2. Let's just neat it up by putting plus signs in there. And to talk you through this, what do? We want to do the I term. Put your finger over the first column and cross multiply. So I'm going to go minus 3 times minus 2 minus 3 times 4. And that's going to be I. So I put my finger over what I was, if you're trying to find I, put your finger over the I column. If you're trying to find J, put your finger over the J column. Trying to find K, put your finger over the K column. Put your finger over the column and then cross multiply. So minus 3 times minus 2 minus 4 times 3. And then we put a negative sign down because it's the second term. Put your finger over the J column and cross multiply. So 2 times minus 2 minus 3 times 3. And that's going to be J. And then we put down a plus sign because it's the third term. Put our finger over the K, and we're going to go 2 times 4 minus 3 times minus 3. That's a K. So this is going to be minus and minus makes plus, so that's 6 minus 12 I. And that's going to be minus 4 minus 9. But that whole thing is minus, so we'll get to that in a minute. J plus 8 minus 9. Okay. And so minus 9, thank you. Yeah. So thank you. So that's going to be 6 minus 12 is minus 6i. And then we have minus 4 minus 9 makes minus 13. And minus makes plus, so that's plus 13j. And then we have 8 minus 9 is like 8 plus 9, which is 17, and it's plus. And what have I forgotten? Units. And let's have a look. This is V cross B, which is F, so newtons. Does that jog your memory about those things? There's another way where you do this big long matrix and you just, continue it and you do the diagonal multiplication. I'm fine with that. If you want to do it that way, you can do it that way. It's just I was traditionally taught this way, so it's the one I tend to go to first, This does not work for more complicated systems. Now, this is not a more complicated system, so it works, but, yes.
Why does it say terameters per second in the options?
Oh, why does it say Tesla meter per second and Tesla meter? Oh, there's an interesting point. Yeah, Tesla and Tera. Yeah, same symbol.
It's Tesla meter?
So that would be Tesla dot meters per second. But let me just stop for a minute there. So let me just stop for a minute there, because it is a force. So I think my brain was like on, recess or something, because it's a force. No, it's not a force. F equals Q V cross B. It's not really a force. It's a force divided by a charge, which is a field. Yeah, which is probably Newton coulombs. Just put the units down that are natural for it. So that's me wrong. So I'll look at it and say, there's nothing wrong with it. Say, oh, that's a Tesla, and that's a meter per second, and I'm out of here. And if it will simplify to something else, hey, fair enough. So can you do that one for me, please? So we're back, and let's see what people were saying. Mainly E, little bit of C. So let's have a look and see which one it is. So what I do is, first of all, I visualize. So 5 coulomb charge carrier has a velocity of that. So here's my velocity, and I'm going to go 1I minus 2J plus 3K meters per second. Region of uniform magnetic field. I just need to draw one of them, so let's just do my B. And this is going to be 3I plus 1J minus 2K. That's Tesla. And then here's my particle, and that's plus 5. And my guiding principle, my principle's equation is that FB, which is a vector, is equal to QV crossed with B. So let's do our V crossed with B bit first. So IJK. And remember it's V, so I've got to find on here my V. So it's going to be 1 minus 2 plus 3. And then B, my B is plus 3 plus 1 minus 2. That's my B. And I've got use over the years, before I commit a whole bunch of brain power, I just double check. So I go velocity was 1 minus 2, 3. Velocity 1 minus 2, 3. And then 3, 1 minus 2, 3, 1 minus 2. Good. I'm comfortable with that. And then I'm going to put my finger over the first column, and I'm going to go minus 2 times minus 2 minus, and then it's going to be 3 times 1 minus 2 times minus 2, 3 times 1, and that's I. Then I put my negative sign. I do it really strong and hard because that's what people forget. And I don't want to forget it, so I go 1 times minus 2 minus 3 times 3. And that's going to be J. I'm going to put the K underneath, plus K. And I put my finger over the last column, and I go 1 times 1 minus minus 2 times 3. That's K. And then I go minus 2 times minus 2 is plus 4, minus 3, I, minus 2, minus 9, J, plus 1, minus 6, K. Then I'm going 4 minus 3 is 1I. Minus 2 minus 9 is minus 11, but that's a plus in front of it, so that's plus 11J. And then 1 minus 6 is 1 plus 6, which is 7. And that's going to be, oh, now I got to multiply that. So this is V cross B. So FB, which equals QV cross B, is equal to 5 times 1I plus 11J plus 7K, which equals 5I plus 55J plus 35K, and that is a force, so that will be in newtons. So that would be, oh I see, that would be E, wouldn't it? And that's why people put down E with a little bit of C. The people with C were focusing so much on the cross product they forgot about. So if you put down C, will you look at your working now, and I want you to answer for yourself. Did you write that equation down? Because I think what happens is people, in their mind, they say, oh, this is a cross product. And they start doing the cross product, and they get the answer. And because they never wrote down what they were trying to find, they don't realize, their brain's not tuned to, I need to find F. But by the act of writing that down, I'm telling my brain, this is what you need to do. And it's there. Once you write it down, it's there. And your brain will kind of like more likely say, hey, you forgot to do something. So, as I say, I'm not trying to teach you. I'm letting you look over my shoulder. You know, the only thing that I would do slightly differently if I wasn't so nervous is I would have probably gone, oh yeah, plus 4 minus 3. And I would have jumped to that step there. I wouldn't have done this thing. But I'm a bit nervous, so I'm going to go nice and steady. Because when I cut steps, I'm more likely to make a mistake, you know. So just watch out for that. Okay, let's use it. So we actually have this apparatus, and we're going to do this experiment probably next week, actually. And what we have is we have a gas-filled tube, and it contains helium. And then we have an electron gun inside here. It's basically a hot wire filament that glows and gives off electrons. And then you have a anode that attracts the electrons and gives them energy, so they fire out like that. And so these electrons want to go in a straight line, and if you don't have a magnetic field, they will go in a straight line. The trick is you can see it in this apparatus because the helium glows as the electrons go through. They hit the helium atoms and they excite the electrons in the shell of the helium atom, and it goes up by 1 or 2 energy levels, and when it comes down it gives off visible light. So all right, so we can see where the electrons are because we see where the glow is. So it's a really nice system, and it will go in a straight line until we put a magnetic field, and it'll start going in a circle, and as I increase the magnetic field, so the circle will get tighter and tighter and tighter. And so I can measure the radius of the circle and use my circular motion physics, together with my kinetic energy physics and my electric potential physics, and I can figure stuff out. And this was used back in the day to measure the charge to mass ratio of an electron. So Millikan figured out the charge of an electron. Well, no, he figured out the smallest charge. Whereas, I think before him, good old whoever it was, Fine, maybe his name was Fine, or maybe it was Beam and people said it was Fine, or maybe his name was, something else, I don't know. I have no idea who did this, isn't it amazing? Anyway, so he or she worked out the mass to charge, the charge to mass ratio. So an electron beam is injected into a uniform magnetic field. Electrons feel the force due to their velocity through the magnetic field. They follow a circular path with a radius that depends upon their energy, which depends upon beam voltage, their mass, their charge, and the strength of the magnetic field. This experiment was performed to determine the ratio of the charge. I'm saying mass to charge, but actually it's a charge to mass ratio of an electron. We're not going to do that at the minute. We're going to derive an expression to give us the radius of this circle. What we say is that the force of magnetic equals QV cross B. How is it that I can go QV cross B to QVB? Why can I just get rid of that cross and just ignore it? What's something about this geometry that lets me do that? They're at 90 degrees. So if they're at 90 degrees, it's just the magnitude of the V times the magnitude of the B. And my centripetal force is equal to mv squared over r. And it's this magnetic force that provides the centripetal force. I don't like using centripetal force. I like using mass times centripetal acceleration, but So I say, well, QV times B is equal to mv squared over r. Rearrange. The radius is equal to the mass of the charge carrier, in this case an electron, times the velocity. If you make it a bigger velocity, it's got more energy, so it wants to go in a straight line more. Over the Q times B. More charge, it's going to curl more. Bigger magnetic field, it's going to curve more. So it works out quite nicely. It's a very nice experiment. You had a comment or a question?
Should we change the mass to charge to mass?
Yes, why not? Yeah. Okay. I mean, you can rearrange it so I'm right, but, I think most of the time people would refer to it as a charge to mass ratio. And this is one of those rites of passage that pretty well most physics students do, and I think it's just a real good experiment. Electron moves through a uniform 8 Tesla magnetic field at a constant speed. The path of the electron is perpendicular to the direction of the magnetic field. The electron forms a circle that has a radius of 5 meters. How fast was the electron moving? So I'll put it on pause. Recording. We're back. We're going to do this together. So let's have a look at this. So here's my circle. I have my little charge here, my Q. I have my R. I have my V. And I have my B. I'm going to put the B like that. Yeah, B's going. I'm going to actually do it like that. I'm going to do B. Now, which way is it? V cross B. See what I did? I just did the right-hand rule so I could get my orientation for my B. I pointed my fingers along the V. I curled it, and I knew that I wanted to get my force, my answer, pointing towards the middle, so I turned my hand so it points towards the middle. Then I curled my fingers, and my fingers have to go into the page, so the B has to go into the page. So what I say is FB is equal to QV cross B, which equals to QVB for an orthogonal system, and C is equal to m times AC, which equals m times v squared over r. So QVB is equal to mv squared over r. So what am I trying to find? How fast was the electron moving? So v squared was equal to QVBR over m. So v squared is equal to 1 times 10 to the 1.6 times 10 to the minus 19 times v. What was my v? Oh, that's what do I find? Hold on. I forgot to cancel something out. Oh yeah, you get cancelled out with you. Sorry. So then B, my B is 8. And R, my R is 5 over M. And M is 9 times 10 to the minus 31. Get my handy dandy calculator. Oh man, I was grading tests before I came here, and I've left it on top of the papers. So this is going to be 5/8 of 40, 9s into 40 goes about, oh, I don't know, let's say 4 times. 1.6 times 4 is about 4. 6 point, it's going to be about 6 or 7. Is it 7.11? And it's going to be times 10 to the 12. Yay! I'm going to, how are we doing? Oh, that's only 46 seconds, so 46 minutes, so I'm fine. Okay. Okay. Oh, so then it's going to be 7.11 times 10 to the 12 meters per second, put in a box. So not bad. You do not have to remember the charge of an electron. You do not have to remember the mass of an electron. I'll give you all that. Frankly, I don't remember, clearly, because I got it wrong, I don't remember that equation. I don't believe in learning equations that I don't need to learn. I know this equation really well, and I know that equation really well, so I can figure out the other one anytime I want. So I'm not going to use up my brain learning things that I already know by a one-step derivation. Yeah? And this tells me the principle. It's not magic anymore. That force equals that force. Boom. I got it done. So don't learn things you don't need to learn. Let's do a little bit of a comparison. We're going to do this several times as the chapter goes on, but let's do a little bit of a comparison and say, okay, electric field versus magnetic field. Electric force acts in the direction of the electric field, yeah, for a positive charge. If I have an E, yeah, F is equal to Q times E, and it's in line with each other, yeah. For a magnetic field, FB is equal to Q V cross B. So kind of different. This is FE. So magnetic field acts perpendicular to the magnetic force acts perpendicular to the magnetic field. Electric force acts on a charge particles whether or not the particle is moving. If you stood still, if you're moving, you're still going to feel this force. Yeah? Magnetic force acts on a charge only when it's moving. And the faster it's moving, the bigger the force. It's like the faster you run, the more it pushes you to the side. If you stand still, you won't feel anything. Amazing. I mean, this is like the most amazing thing. And electric force does work in displacing a charge. Yeah, the force is in direction with the displacement, so work gets done or work is done on it. In this case, no work gets done or no work is done on it because they're perpendicular. So it's kind of interesting. Just similar but different. And whenever you get things that are similar but different, always put them down on the same piece of paper and compare and contrast them. Let's watch this in action. So let's take a piece of wire. Wire that conducts charges is just a whole flow of, we don't need an electron beam, just have a piece of tin foil. Go and get some aluminum foil and connect a battery to it. You've got a stream of electrons, just like an electron beam. It's just you can't see it. And put a magnetic field across it. Get a couple of magnets, put it across it, and then see what happens. Well, there's electrons in here, and when there's no current flowing, nothing happens. So here I'm drawing a schematic diagram. I want to show the magnetic field going away from us. And so I show it as a whole bunch of X's. Now, I tend to put it X's in little circles, but I can see how that gets really old really fast. So the book tends to use just X's. Yeah, I hope they don't use just dots because that's a bit off. And there's no force in any direction because there's no motion. But if I am positive charges moving upwards, F is equal to QV cross B. So you point in the direction of the V, which is up the page. You curl your fingers in the direction of the magnetic field, which is into the page. And so your force is in that direction. So there's my force. And if you get the current to flow the other way, then you have V, and my V is now downwards. So point your fingers downwards, and then curl your fingers into the page, and your thumb is pointing to the right. So there's the force. And this is quite easily demonstrated, actually. Piece of tin foil. Get some tin foil and cut it, aluminum foil, and cut it into a long strip. Hang it vertically so it's not supporting its own weight. Just get a pretty strong magnet and run a pretty high current. I mean, it's not something I'd suggest you do at home, but it will move. Okay, let's look at a segment of the wire. So here's a segment of the wire. It's like a tube, isn't it? Oh, sorry, cross-sectional area. And we have a charge carrier, and it's moving with a certain drift velocity. Remember drift velocity? And it's in a uniform magnetic field. Now, frankly, this uniform magnetic field is going into the page. And I don't know why they kind of gave you a three-dimensional drawing here suddenly, but it is into the page. So my V is to the right, and my B is into the page, so my force is upwards. So this is a vertically upwards force because of that V and that B. Okay? And so we say, consider a segment of straight wire of length L, so there's my length, and cross-sectional area A, so I got the cross-sectional area, that's at the end, carrying a current I in a uniform magnetic field B. Remember that the charge carriers move with a drift velocity, and the force on one moving charge must be QV cross B, while V is going to be the drift velocity cross B. For a stream of electrons of charge carriers, then we just have, we have the force on one of them times how many of them there are. And if we have N per unit volume and a certain volume AL, that's how many of them there are. And then I say, remember that I is equal to NQV times A. Remember I did that in the last chapter or the chapter before. So substitute in, and we have an N, an A, an L, and a Q. An N, an A, not an L, sorry. A Q and a V. N, A, Q, V. So that leaves me my L, and it leaves me my B. And so with a little bit of sleight of hand, I give you that FB is equal to I into L cross B. L is the length of the wire. I is the current flowing through the wire. B is the magnetic field. And that enables us to do calculations when we're dealing with a length of wire with a certain current flowing through it in a magnetic field. Notice the chapter's about magnetism, not about length. This is not a chapter about let's study length in various guises. Let's study magnetism in various guises. And magnetism is to the back. Yeah. What I'm going to do is I'm going to stop. Pause. So we're back, and so we did this. So just a couple of things about this. So what did I do? I basically drew a diagram and I said, here's my wire and here's the magnetic field and my current is 5 amps. And then I said, well, I know that, well, F equals QV cross B. By analogy, if you like, F is equal to I L cross B. Not really analogy, but it's a similar form. And I want to do L cross B, so I did IJK, and I put down my L. And L, I didn't have it. I just said it was 3 meters in the positive X direction. So that's not a vector. So I had to make that into a vector, which I did do. I made it into a vector, and then I crossed it with my magnetic field vector, and then I multiplied that result by my current. And just as I sit here, so the first thing that we realized was that the answer that is truly the answer is not any of the choices. But the second thing that I've just noticed, and you've probably noticed as well, is that I doubt very much whether 3I plus 4J minus 2K has a magnitude of 6 Tesla. Maybe I'm wrong, but I'm giving you a magnitude without a direction. Then I'm giving you IJK. And from a teacher's point of view, those two had better be consistent with each other. And just as I'm sat here, I'm not sure they are, you know. But can you see how, if you know the cross product and you know the equation, this is done. It's like we're going to use these same skills over and over again. So let's stop there. We'll take a break.